I'll introduce codes and error correcting codes. And so first, just a word about terminology. So for us, a code is going to be a collection of code words. And what I mean by code words is going to be, well, strings. And what symbols are in the strings? For us, it's going to be always binary. So binary strings. So as an example of a code, I would just mean something like this. A set of like strings like this, 0, 1, 0, 0. That would be a code. So you could have in a code strings of all different lengths, but for us, most of the time, we're going to focus on codes that have strings of a fixed length. So here, they're all of length 4. And then that's called a fixed length code. But I won't say all of those words every time because most of the time, they're fixed length for us anyway. And what do you use these codes for? So you're going to use them for sending messages. And the idea is that a message which is transmitted properly, i.e. has no errors in it, will consist only of code words from the chosen code that you've decided to use. So a message consists of code words. And so for this code above, if we wanted to send a message to someone, a valid message would be, this, 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 this. There, that's a valid message. But an error could happen in transmission. Something goes wrong. So an error could happen. And then it could end up that the person you're trying to send the message to would receive something like this. 0, 0, 1, 1. 0, 1, 0. Now, if you look up at this code, this and this are both not contained in our original code, and so something has gone wrong. For instance, you know that this is an error, you know that this is an error, but there's something really bad about the code we've chosen to use. We don't know whether or not this is an error, and we don't know whether or not this is an error. And here's what I mean by that. Because our code contains both 1, 1, 1, 1 and 0, 1, 1, 1, we don't know whether the person who sent us the message really intended for a 1, 1, 1, 1 to be here. They could have intended 0 and 3 ones. And if there was an error in this first bit, we would have received 4 ones and thought that that was the intended message. And so this code, C, cannot detect single errors in code words. So here, C cannot detect errors. So I'll say single bit errors, just to be clear. And what I mean by single bit errors is that it can't even tell us if there's been an error of 1 bit in one of the code words, because it could have been that this 0 right here changed to a 1, maybe in this bit up here, and we're none the wiser that that happened. Okay. We can do better than this, though, by choosing a different code. So what we could do instead is we could try some new code, C prime, and let's say that instead of the code I just gave an example of, we decided that all of our messages would consist of code words from this collection. All right. Then suppose that we get the message as before. So then suppose you get this message. Actually, I'll just change that so it's there, and this. Okay, then as before, you can look at this and say, okay, this is an error because that is not a valid code word. But now you can also look at that and say, there is no error here. That is, if we're assuming that there's at most one bit change per code word in the message that we've received. Then we can look at this and be certain there's no error in this first code word. And the reason for that is because the two code words that caused problems last time have been changed. Now we have this and this. And to get from one to the other would require a change of 2 bits instead of just 1. And if we're assuming that there's at most 1 bit change per code word, then that can't happen anymore. So this new C prime, it does detect errors in some sense. And the sense is, if there is 1 bit change per code word, then we know that there's been a bit change. So I'll put single bit errors. Okay, now let's make formal what it is about this code C prime versus C that allowed us to find that error. So sort of how do we know that an error happened and what was the reasoning behind it? So before I can say anything formal, I have to introduce some notation. So if S and T are binary strings of the same length, then what I want to do is use DST to be the number of different bits. What I mean by that is it's the number of bits that you have to change to get from S to T. So in the first example where we had a code where you could change a single bit to get from one word to another, that was a problem. And so what I'm using DST to denote would be 1 in that case. All right. This is called the Hamming distance between code words. So Hamming distance. So, just as an example, to be completely concrete, the Hamming distance between something like 1, 1, 1, 1 and 0, 0, 1, 1. So this is from the good code that was able to detect errors. That would be 2. Because to get from one to the other, you either have to change both these zeros to ones, or you could change both of these ones to zeros. In either case, there has to be 2 changes in one of the words to get from one to the other. Okay, now the reason that C prime was able to detect errors in our previous example was because it took 2 changes to get from one word to another. So C prime detected errors. The way we would write this in our new notation would be because DST is bigger than or equal to 2 for all S and T in the code C prime. But it could only detect 1 error per code word. So what you would say is you would say that C prime is 1 error detecting. Because 1 error per code word could be picked out. And in general, though, there is a notion of K error detecting. So in general, you could have a code that would allow you to determine when there's been up to sort of K mistakes per code word, and you would still be able to pick out exactly which code words had those mistakes. So let me write down what that requires. So in general, C a code is K error detecting. And we'll write it in terms of the Hamming distance between strings. If 0 less than dst less than or equal to k, and if s is a string in your code, or code word, then the distance between s and t being less than or equal to k implies that t is not in your code. So what this means is, if you start with a code word and you make k or fewer errors on it, then the resulting new string is not in your code anymore. And that's what's going to allow you to detect errors, because if there have been k or fewer errors in transmitting some code word s, you'll be able to just look at it and say, well, that's not in my code, that's not a word I'm supposed to be seeing, so that must be the error. If you could get another word in your code by making k or fewer errors, then it wouldn't be error detecting anymore, because one word could change to another one that's not intended and you would be none the wiser. Just like in the example where we had 0 and 3 ones changing to 4 ones. So let me give an example of something that's k error detecting where k is bigger than 1. So example, let's try this code. So C is 1 1 1 1 0 0 1 1 0 1 and 5 zeros. Okay, now what you can do is you can check that the distance between any two S and T in this set is bigger than or equal to 3. I mean, just check all the pairs. And in fact, the distance between these two, 1, 2, 3, 4, 4 ones and a 0, and 0, 1, 1, 0, 1, the distance there is exactly 3. So you can get from one code word to another by making 3-bit changes. But if you make 2, you're not going to get from one code word to a different one. So let's just write out the sort of formal mathematical sentence that means this code satisfies. That means that if k equals 2, then the distance between s and t being less than or equal to 2, so that's our k right there, and s being in C, that's going to imply that t is not in C. And so if you compare that to the phrase up here, the mathematical phrase, we can see that with k equals 2, this code satisfies that mathematical statement. So check. This means that C is 2 error detecting. All right. Now let's just play with that code C. Let me write it down here so that you remember what it is. Let's just play with this code C and imagine that we're using it to send messages. So we can see how the fact that it's 2 error detecting influences how we think about the errors and the messages that we receive. So imagine we receive this message. So no problems there, no problems there, problem there. So this has to be an error, because we know that this is not one of the valid code words from our set C. And we know that these other two, these are not errors, because if we're thinking that there's only going to be at most 2 errors per code word, we can't have taken one code word in C and accidentally arrived at another one by making just 2 errors, because all of the words in C are 3 apart. All right, but let's inspect this a little bit closer. So it could have come from 2 different words with 2 different kinds of errors. So it could have come from, Well, it could be that the sender intended this code word in that position, and then the errors were here and here. Or it could have come from this code word, and then the errors were here and here. So we do know that there's been a mistake, but we don't know what the mistake was. So we can't correct the error. So we cannot correct for this mistake because there's ambiguity. So what we need is the notion of an error correcting code. So error correcting. And this is going to be sort of like a strengthening of detecting, where we ask for code words in our code to be even farther apart, so that if there are only a few errors per code word, then we can actually say which code word those errors must have happened to. And I'll cover that in the next video.